Hello, my name is Amit Paz. I'm from the University of Vienna. This is joint work with Uri Meir from Tel Aviv University and Rui Schwartzman from the Japan Advanced Institute of Science and Technology. And it's about models of smoothing in dynamic networks. So the main computational problem we are interested in this work is flooding in networks. In this problem, there is one unit, one processor that has to propagate information throughout all the n unit or n node network, which is represented by a node graph. And we know that if the network is static and doesn't change over time, flooding will take roughly diameter time. But we're interested in dynamic networks where there are changes over time. So first, the message propagates from a unit to its neighbors, and then the topology of the network changes. And this continues again and again. Now, under this setting, and with the extra assumption that we always take that the network is always connected, flooding will take at most n-1 rounds. And this is just because in each round, at least one new node learns about the information. But in the worst case, this can indeed take n-1 rounds. Of course, if the diameter is n-1, but even if the diameter is constant, say if you have two stars, one with the informed nodes and another with the uninformed nodes, connected by a single edge, and every time an uninformed node becomes informed, you move to the left, it will look roughly like that. First, only the leftmost node knows the information. And then when the information propagates, the topology of the network changes, and there's a new star on the right. And again, we have one star on the left of informed nodes and another one on the right of uninformed nodes. And note there are also many changes between every two consecutive communication graphs here. And indeed, these are two stars connected by an edge, so the diameter is 3, but flooding will take n-1 rounds. Now, how long diameter really takes in real systems? So on the right-hand side, we have the worst case, which is n-1 rounds that I just presented. On the left-hand side, we have the random network case. If the topology of the communication graph is random under accepted models of randomness, flooding will take roughly logarithmic time. And it seems like in reality, flooding takes something in between, not as fast as log n, but also not as bad as n-1. And the question is how to model such systems that are adversarial, but not really worst case adversarial, but have also some randomness in them. And one solution proposed for this is smoothed analysis. This is a way to model adversarial systems that have some random perturbation on the input or on the system as well. So this idea was presented by Spielman and Tang, and they presented this in the centralized setting to analyze pivoting rules in the simplex algorithm and understand why the simplex algorithm performs better in practice than theory would predict. And then there were many other works on smoothing in the centralized setting. And in this, exactly 5 years ago, Diniz et al. Presented the model of smoothing in dynamic networks. And this is the work we build upon today. Very recently, another work studied building a minimum spanning tree, again in smoothed dynamic networks, but with a slightly different model where there's actually no adversary, but just these smoothing edges from round to round. Now, I just want to emphasize that there is a big difference between the centralized setting, where there is input that is smoothing and then smoothed once, and then it's being analyzed and the algorithm runs on it, and the distributed dynamic setting, where the input is a sequence of communication graphs, and each of them is being smoothed. This is a continuous process where the smoothing happens again and again, and not just once as in the surface. So Diniz et al. Started by presenting a model of smoothing. And they presented a model that's called integer noise. Here, the adversary picks a sequence of communication graphs, and each of the communication graphs is being smoothed by that it's being replaced by another communication graph on the Hamming ball of radius k around it. And we just exclude graphs that are disconnected in this Hamming ball. Now note that most of the graphs in this ball have distance of almost k. different edges from the original graph. So most of the time, we take a communication graph chosen by the adversary and replace k of the edges, add or remove k of the edges in this graph. So it will look roughly like that. The adversary chooses a sequence of communication graphs, and then the smoothing process smooths each of the communication graphs by adding or removing roughly k edges from it. And then flooding will happen on this sequence of smoothed communication graphs. Now, under this model, Dinitz et al. Proved that flooding will take roughly n to the 2/3 over k-third rounds with high probability. All the results today are with high probability, where the probability is taken on the smoothing decisions, on the random decisions of which edges to add or remove. And this already presents a very interesting phenomena, or a very curious gap between the case of no noise, k equals 0, where flooding takes n rounds, as I mentioned before, and very minimal noise of k equals 1, maybe just one edge being added or removed in each round, where flooding will take n to the 2/3. So we go down from linear to n to the 2/3. That's very surprising. And this was the first question we were set to answer in our work. Other questions had to do with the model of smoothing. What happened, for example, if the adversary is adaptive and sees the changes of smoothing before choosing the next communication graph? And second, what happened if the noise is responsive? That is, if the adversary doesn't change a lot, there's also less noise. Because it made sense to us to say, okay, if the network changes a lot, there's also a lot of smoothing on these changes. But if the network doesn't change, if the adversary doesn't do anything, there's no reason to have something smoothed on the network and have these random edges. So let me present you a few of the models we discuss in this work. We present several models. The first is of adaptive adversary. So we extend the model of Dinitz et al. By saying, okay, you still have k random edges, but the adversary picks a graph, and then the graph is being smoothed, and then the adversary sees this smoothed graph and chooses the next one, and then the next one is being smoothed, and so on. So the adversary knows the previous smoothed graph before choosing the next one. And again, the noise is just k random edges, roughly. Next, we go to what we call proportional noise model. Here, the number of edges being changed by the smoothing process is proportional to the number of changes made by the adversary. So if the adversary doesn't change anything, there is also no smoothing in the network. While when the adversary changes a lot, there is a lot of smoothing, a lot of random changes as well. If the adversary changes few edges, there is also a small random perturbation, small noise. And this has both the adaptive and oblivious adversary versions. And last, there is a model that we present of targeted noise. Here we think of an adversary that tries to change the network, but doesn't always succeed. But in this case, the noise can only happen, or the smoothing process can only happen on edges that the adversary tries to change. So if it doesn't change anything, nothing happens. But when the adversary does change some of the edges, only these edges can be smoothed by being added or removed, opposite to what the adversary did. So if the adversary tried to remove the bottom edge from this graph, then maybe it's not being removed, but it's the removing process is being reverted by the smoothing process. And again, it has both the oblivious and adaptive adversary versions. So these are our main results. The top ones are for non-responsive noise, and the bottom are for the responsive noise model. And let's go over some of them. So first, I want to talk about the non-responsive noise with oblivious adversary. This is more or less the model by Dinitz et al., but with a few changes. So first of all, most interestingly maybe, we present a model of fractional noise, where k, the number of changes, can be a fraction. And then we extend the range of k to start from 0 and not from 1. And also, for larger values of k, it can be fractional, but the most interesting case happens when k is between 0 and 1. There, one edge changes, but only with probability k. And we see that flooding takes n to the 2/3 over k-third, just like in the work of Dinitz et al. which means that so we extend the same function, we extend the model and then get the same function representing the flooding time. Also for these fractional values of k, which indicates that our model is probably good or correct. Another thing we do is improve the analysis, which shaves off polylog n factor and makes it much simpler, makes it slightly simpler, and allows to analyze this fractional k case. And now let's compare these upper bounds for the oblivious adversary with the same model, but with adaptive adversary. So here we prove a lower bound that says that if the adversary is adaptive, flooding will take linear in n time, and not just n to the 2/3. So the idea to have an adaptive adversary really makes a lot of difference, and it gives a different model with a polynomial in n gap between the flooding times. Now let's talk about responsive noise, where the amount of noise depends on the changes. So first, we have the proportional noise, where only the amount depends on the changes, but not the location of the changes. So first, note that we change the k parameter, the number of edges changed, to epsilon, which is the fraction of changes with respect to the amount of changes made by the adversary. So this, of course, requires to analyze fractional noise, as I mentioned before. And also note that here there will be different amount of changes in each round. It's not as before, k changes again and again, more or less, but many changes by the adversary means a lot of smoothing. No changes by the adversary means no smoothing. And still, when the noise is proportional but scattered around on the graph, you see the results could be similar in some sense to the previous ones when you have the n to the 2/3. Although we have another parameter here, which is the diameter of the graphs, which comes into play. And the diameter comes into play much more in the targeted noise model, where the noise happens only on the edges that the adversary changed. This is on the bottom here. And here, if the diameter is small, flooding will be super fast, roughly log n time, with a function of the diameter also. And this is because the adversary may try to prevent the flooding by changing the graph, but the acts that the adversary does are maybe reverted by the smoothing process. And this is exactly the idea of targeted noise. On the other hand, as soon as the diameter gets to logarithmic, or of course more, then the adversary can prevent flooding much more and up to linear time actually. So the flooding time really increases a lot from small diameter to even logarithmic diameter. This is because when the diameter is at least logarithmic, the adversary can force changes by repeating them again and again until they really happen, or they happen with high probability at least. And this way you can force the flooding to happen only on paths of, let's say, half diameter. And then the adversary, when he creates such a path, it doesn't change anything more, and there is also no random noise. So he creates a situation where there's just a path to flood on, and nothing else can change even randomly because the noise is proportional to the changes of the adversary, who doesn't do any changes, so there is no noise. And after going over this path one by one, he will change the graph to have another path, where again, flooding will have to happen on the nodes one by one, and we build a lower bound graph built on these ideas. And today I'll just talk about the upper bounds in the oblivious adversary case, an extension of the Diniz et al. Upper bound, and then analysis for the adaptive adversary cases. So let's see how we prove these upper bounds. So we have one node U with the information. I want to see how long it will take for the information to arrive to some other another arbitrary node V. Oblivious adversary with k random edges per round, more or less. And we choose a parameter R, which will be, of course, the flooding time, which is n to the 2/3 over k third, and analyze what happened when you run for 3R rounds. So 3R will be the flooding time that we claim. So first we look at the first and the last R rounds out of these 3R. So in the first R rounds, there will be a set SU of nodes that are being informed. Now, since all the communication graphs are connected, in each round, a new node will be informed, and after R rounds, the size of SU, the set of informed nodes, will be at least R. And this set is actually not predetermined, but it's a random variable depending on the choice of the adversary, which are predetermined because the adversary is oblivious, but also on the random smoothing process and smoothed edges. Okay, so we have one random variable, SU, that has a set that has size at least R. The more interesting set is SV. These are nodes that can inform V in the last R rounds. And to find this set SV, what we do is use heavily the fact that the adversary is oblivious. So we can look in advance on all the graphs that he chose for these rounds, and then on the smoothed version of them, and then look at the flooding process that would start from V at round 3R and go backwards in time. And ask which node would be informed if we start flooding from V and go back in time. And then we again get a set SV of at least R nodes. And this is again a random variable. And the idea is if we hit any of the nodes, if any of the nodes in SV gets the information in round 2R or before, then in up to round 3R, V will also land information and we win. We manage to do flooding. So now we are only left with the question, will the nodes of SU inform the nodes of SV in the intermediate R rounds? So what happened between round R+1 to round 2R? We want to analyze if the information propagates from SU to SV, and we'll only look at the simplest way to do this, which is having an edge between SU and SV, not considering paths between them. So let's take just one single round and ask what's the probability to have an edge between SU and SV. Now, these sets both have size R, so the number of edges, potential edges between them is R squared. The total number of potential edges in the graph is N squared. And we can prove, and we prove with some lemma actually, that in a single round, an edge between SU and SV appears with probability K, which is the smoothing parameter, times R squared over N squared. And then if you take all the R rounds, you can see that with high probability, an edge between these sets will appear at least in one of these rounds. And all this analysis also holds for fractional K. Now, if one of the edges appears, then we are done, because there is some edge between X in SU and Y in SV. And then flooding will be in the first R round up to X. In one of the rounds when there is the edge X, Y, there will be flooding from X to Y. And then in the last R rounds, the information will propagate from Y to V. Okay, and now, since this holds for any node V, we can take a union bound and show that after 3 R rounds, which is n to the 2/3 over k3, flooding will happen on all the network with high probability. And this is the proof that we take from the previous work of Dinitz et al. And extend and simplify a bit. And the next question is what happens if the adversary is adaptive? Because here, picking SV highly dependent on the fact that the adversary is oblivious, and we can take the time back. But if the adversary is not oblivious, then as soon as some node Y is being informed, the adversary can take it away from V and make sure the information doesn't propagate or doesn't propagate fast from this node Y to V. So adaptive adversary requires a slightly different analysis. And basically, it requires us to take higher value of R and omit the whole set V. So now we have R, which is larger, n over square root k. And we analyze only 2 R rounds. In the first R rounds, again, there is the set SU of nodes being informed, and the size of SU is still at least R, just as before. And now we analyze the probability that a random edge appears between SU and V itself. And there is no more a set SV. And then a similar lemma shows that this event happens with probability KR over N squared. Note that it's almost the same, but here we have R and not R squared. And this is why we had to take much larger R. And of course, if this happens, then this node in SU, say X, learns the information in the first R round, and then it propagates it to V in one of the rounds between R and 2R when there is the edge X, V. And in R rounds, this happens with high probability with a similar analysis, which means that flooding can be done in 2R rounds to all the network, again by union bound. And while this analysis seems with a lot of redundancy, actually it's not. At least in terms of n, we have corresponding lower bounds, and you need time that is linear in n to do flooding when the adversary is adaptive. And this is all the technical part I wanted to present. So just to conclude, we present many models of smoothing in distributed dynamic networks. And if you want to apply smooth analysis to some real network, you have to really understand the parameters of the network, because what we show is that slight different models give really different results. So there is really a difference between these models. They're not equivalent, and they should all be studied in some sense. And the open problems is to study, first of all, other problems, say heating time of random walks. And this is a bit similar to what we studied. Another type of problem is load balancing on building a minimum spanning tree. You know that here, the algorithm itself plays a much more crucial role. If flooding or random walks is a process that just happens and depends only on the communication network, load balancing or minimum spanning tree construction also depend on the algorithm itself. So we have to define what exactly the algorithm does. It's not that it sends information or walk randomly in the graph. And another type of problems is to have application-driven models of smoothing. It's not even clear that we exhausted all the possible models of smoothing. I will stop here, and thank you very much.